Hi, in this video I'm going to introduce our work on leveraging vision transformers for pixel-wise dense prediction tasks. This work was conducted at Intel Labs by René, Ranftl, Alexey, Bochkovskiy and Vladlen, Koltun. Dense prediction is the task of assigning a label to every pixel in an input image. Common tasks that fall under this general term are semantic segmentation, where every pixel is assigned a class label, or depth estimation, where every pixel is assigned a depth value that either denotes the distance of a seen point from the camera or the relative distance between pixels. Dense prediction is commonly solved using variants of fully convolutional networks that graft a decoder onto a backbone network that was pre-trained for image classification. A fundamental limitation of fully convolutional networks is the basic operation itself. Single convolutions have limited receptive field size. This means that the network can only see a limited amount of context in the early stages of processing. Larger receptive fields can only be acquired by passing through consecutive convolutional layers of the network and interleaving downsampling layers to keep memory requirements manageable. As features pass through the layers of the encoder, a larger receptive field is acquired. However, the downsampling operations induce a loss of detail in the deeper layers that have larger context. In this work, we propose to leverage vision transformers instead of convolutional backbones to perform dense prediction tasks. Our dense prediction transformer architectures have a global receptive field throughout the main processing stages and provide high feature resolutions also in deeper layers of the network. We show that these properties are especially useful in the context of dense prediction in order to disambiguate visual content and to provide fine-grained dense predictions. Our network leverages pre-trained vision transformers as backbone networks to extract feature representations. The vision transformer architecture was recently introduced by Bochkovskiy and colleagues as a novel architecture for image classification. It treats an image as a set of patches, called tokens, that are first embedded into a feature space and then processed by a cascade of transformer layers in order to produce updated representations of the tokens. The transformer layers use multi-headed self-attention as their fundamental operation. Multi-headed self-attention is an operation that relates each token to every other token in the image and consequently has a global receptive field. The vision transformer does not use downsampling operations in its intermediate stages and thus supports fine-grained feature maps also in the deeper layers of the network. To leverage the tokens that are produced by the vision transformer for dense prediction, we reassemble the set of tokens at various stages of the backbone into image-like representations. We first integrate the features of the auxiliary class token that is emitted by the backbone into all the other tokens. We then spatially concatenate the tokens and resample the resulting feature maps before passing them to the decoder. The decoder iteratively fuses and upsamples the reassembled feature maps from different stages and produces the final dense prediction using an application-specific output head. The feature maps from consecutive stages are fused using residual convolutional units, followed by bilinear upsampling. Transformer-based architectures are known to unleash their full potential when a large amount of training data is available. We first test dense prediction transformers on the task of general-purpose monocular depth estimation, where we train our networks using the MIDAS training protocol on a large-scale metadata set that consists of about 1.4 million images. Our experiments show that dense prediction transformers outperform existing convolutional networks on this task by a large margin. Dense prediction transformers outperform the state-of-the-art by up to 28% on average with a comparable amount of compute and latency. We additionally show that our networks can be fine-tuned on smaller datasets such as NYU V2 or Kitty, where they also provide state-of-the-art results. When comparing their predictions to existing fully convolutional networks, we see large qualitative improvements in terms of global coherence and predictions that are significantly more fine-grained and detailed. We also find that dense prediction transformers provide better results than their convolutional counterparts when performing inference at higher resolutions than the training resolution. This is an effect that can likely be attributed to their global receptive field size. We further train our networks for the task of semantic segmentation on the 8820K and Pascal context semantic segmentation datasets. For this task, we again observe clear improvements in terms of global coherence and the details of the predictions. Thanks for watching. Please have a look at our paper to find more details and experiments, and visit our GitHub page if you want to try the models yourself.